21,000 cropped images with 46 distinct aircraft, and they came in 19,000 different sizes, roughly. Their widths could range from 11 to 8,000 pixels, and their heights range from 6 to 4,900 pixels. Now, a thing is, a convolutional neural network requires consistent sized input, so we had a few possible pre-processing techniques we could use. Our two main approaches we used were resizing the images, specifically to the average width and average height, which was about 700 pixels by 340 pixels, or we could try and scale down the large images and make sure we pad them all to a consistent size, which was 1,000 by 1,000 in this case. And YOLO v9, being an image segmentation algorithm, didn't really need pre-processing on the original dataset, so we did not provide that, although we did have to change annotations in order to work. And here we have some examples of the pre-processing. So here we have the original image that we chose for this example, being an aircraft on a magazine. And when we resized it, here are the approximate dimensions. It's a little warped due to having to put it in the slideshow, but is what it looks like roughly. And over there on the end, you can see it being resized and then padded with black on the edges, which preserves the aspect ratio. So, as part of model architecture and design, we started with the convolutional neural networks, which were custom made, simple, and very lightweight. And that was primarily because we needed them to be quick to train because of our hardware and time limitations. So they consist of 3 convolutional layers and 2 fully connected layers. And they were made using PyTorch in VS Code with Anaconda as a package manager for PyTorch and the like. And we had to train them on laptops for a while. And then for YOLO v9, that is actually an established algorithm. It's very modern, as in it came out like a month ago. And it is also very large. I believe it's about 9,000 players, I read. And it can ID multiple targets within a single image, making it very useful for aircraft identification. And we tried to run it in Google Colab in order to get access to GPUs to train it faster, but unfortunately we were timed out. We tried to train it on CPU, but that was incredibly slow, taking about 7 hours for a single epoch. And so we unfortunately did not bring this plan to completion. Now, for training and evaluation, we tried an 80-20 and a 70-30 training testing split of images. So 80% of our entire data set was set aside for training and 20% for testing. And for the other convolutional network, it was 70%, 30% to speed it up a bit. They were randomly selected from each class to ensure every class was preserved in the training and testing data sets, and to give us a wide variety of images to train on. And then we made sure to evaluate on each class. And our results were that our resized data set being fed into a convolutional neural network had a 44% accuracy on the testing data set. That was images it had never seen before. And for the convolutional neural network trained on the padded images, we managed to achieve a 7% accuracy. But that was trained far less than the first one. And unfortunately, YOLO v9 did not complete in time for this presentation. So, explain the big reason why resized had such a better result was that it managed to go through 9 different versions over the course of a few months. Our baseline only had 1.9% accuracy and was derived from a pre-existing model I had from a previous project. The second version was larger and was trained for longer and managed to achieve 5%. For version 3, a different size of images was tested, only to find that it resulted in a loss. Similarly, we tried to go even bigger for v4, and yet it also too had a loss. So clearly, a smaller model was going to work better if we trained it for longer. And that's how we wound up with v5, v6, and v7, each gaining some accuracy. At v7, there was a roadblock, and I believed it was due to having a way too high learning rate. So reducing the learning rate, which is roughly how fast it trains, managed to get us our best result at version 8. We tried a version 9, but with a lot more epochs, a lot more runs through the through the training data set. But unfortunately, it trained a little too hard and wound up overfitting, losing a bit of accuracy. So v8 was inevitably what we went with. If we had more time, we would be obviously continuing the other 2 approaches, putting more time into getting padding enough training and actually getting YOLO to be brought to completion. And as well, we could further iterate our algorithm for handling the resized data. And I'm going to bring this over to Daniel for the additional applications of this technology.
One last slide on this. We were asked what good is this technology for in other areas. I've worked with the Naval Research Lab for 30 years or so, and we work with radar data a lot. So I instantly thought of a lot of our radar data sets could benefit from this because we're trying to recognize different types of emitters in digital RF recordings. So those kind of digitized RF recordings or spectrograms or just characteristics of pulse radars would benefit greatly from a convolutional neural network type approach of recognizing the source of an emission. And then there's all the other things that are already well publicized in the literature for facial recognition and video processing. This is already in use in many places. You can use it just on sound data. If you digitize data from an audio stream of any sort from a microphone, you can use it for network traffic analysis. If you just want to capture IP packets on a network and find out what kind of patterns are in there, these neural networks can pull that kind of stuff out. And it's just the beginning of all the applications you could have. Okay, so next slide, we have a small little demonstration program we built out of Python and TK Inter graphics. Here's two slides that show an image that's actually matching the correct identification and one that didn't match the correct identification. But we can show you this live now if everything's well. Data sets, here's our recognizer. Okay. So we'll just take the F-35 data set. You can take any data set you want, grab a picture, throw it into here, and it catches up. There, it says it's an F-35. I'm saying. Okay. The room can hear me. Okay. So I stuck an image into a recognizer. This is the truth value up here. It's an F-35, and the recognizer says, oh, that's an F-35. And I'm obviously taking from the F-35 data set. So if I pull this out of the way, pull this one, new one, that's also an F-35. This one, that's an F-35. This one here with the canopy up, oh, that one doesn't match, even though that's an F-35. So pull another one in. There's a positive. Here's a positive. Now, you just think I'm hard coding everything. I'll go over here and look at the A10s. Grab this first A10 picture, and it says that's an A10. Boom, boom. Grab this one right here. Stick that in. That, believe it or not, could see those big old engines and say that's an A10. And eventually I will get ones that don't match depending on what you've picked. Is there an A10 in there? Apparently there is. There's one that doesn't match. Okay. So you're invited to come and try any of these pictures you want. Now, the caveat I have on this is the entire crop data set. So some of these images were used for training. This is not from the testing set, which was held aside. So that's our version of a image recognizer that produces pretty much 44% accuracy. It's a little bit higher accuracy on these files because some of these have already been trained. And that's our presentation.
Thank you. That was team 111%. Judges, do you have any questions? I failed to indicate that we would allow question and answer after each presentation. So Jonathan? If you don't mind using the microphones, because the virtual teams can't hear if you just push the button. Thank
Can
you.
you hear me?
Yes.
Yes, so did you only try validating with other pictures of aircraft, or did you try maybe pictures of dogs or something like that?
The data set the data set we were provided was entirely aircraft. It was what we believed the intention of this project was, and so we entirely focused on aircraft.
Okay, no, this is a question of, I know a lot of, particularly with, when it comes to ML applications, if you force the algorithm to only look at a subset of classes, then when you expose it to something outside of that, you can get false positive and really strange results. Just curious if you had tried testing your model against a more diverse set. Okay. You also mentioned that you tried to get things working on Google Colab and using a YOLO approach. I think that's really awesome, but unfortunately you said you were unable to get that to work at all. Okay.
My runtime unfortunately ran out as it's not paying for it.
Right.
So I was unable to get further than like 2 hours of the training.
Okay. Anybody else have any questions?
I got them.
Say it again, say it again to the microphone.
Yeah, I got it. I was about to say, on your YOLO V9, you said it didn't require any pre-processing.
Operate on the original data set, which came with annotations that pointed to where each aircraft was, which is how the image segmentation algorithm like YOLO works. It would take the images automatically decide them for you. I believe I set it to specifically 256 and then it would use the annotations to identify where the aircraft were for training, and then would try and give you those annotations of both where and what the aircraft were for testing, whether should I have gotten to.
Oh, for sure.
And processing needed to have consistent size.
Okay.
Thanks for reminding me. So you mentioned your data processing, pre-processing techniques. I think you outlined padding as well as what was the other one that you think you mentioned? Resizing, yes. Did you try, were there any other possible ways you could maybe have manipulated the image? Maybe if you take a look at the data set, did you maybe mess around with the colors, or why didn't you try some other techniques? Why did you choose those two?
As has been said, the easiest way to get an AI to recognize an image is that if a human can recognize that aircraft. So if you mess with the image too much in unexpected ways, you're going to get some unexpected results. I wanted to stick to a few simple solutions here, just focusing on getting a consistently sized input. Okay. So we stuck entirely to just getting that consistent input for now. Further pre-processing could be investigated.
Did you take a look at your data set and like investigate what were some of the biases in your data set potentially?
Well, obviously our data set was uneven among a variety of classes. I believe the American aircraft were especially common, which might explain why it has a particularly high accuracy on those. So it's obviously going to be a little unbalanced between the classes. But we did train and test it on everything and made sure that every class was represented in both training and testing. So it should hopefully work for everything to at least some extent.
Right. So, okay, no, that's good. So you did investigate the biases in your data set. That's important. I have more questions, I think.
I have questions.
So did you try to come up with any means to offset? So it's usually a lot of US aircraft. Did you try out the foreign aircraft? Did you?
No, we did not, because we were focused mostly on keeping this one data set together, and trying to find other data sets and mix them in would make this more complicated.
I mean, did you try anything like image clipping or?
We did actually try that on the resize data set to expand our general scope. We gave every image, I believe, 2 flips, horizontal, vertical, and both horizontal and vertical. iterations to make our data set way larger.
It's in the training data. We didn't mention that.
Yeah, I guess we forgot to put that on the slides, or we removed it when we were editing it.
Okay,
Yeah, we had 4 reflections on the resized data set.
good, nice.
Any other questions? Okay, thank you. Once again, thank you, team 111%. We will next go to the military aircraft ML model team. And if you just make sure you speak into the mic, just because then the teams that are online can
Testing
hear
1, 2,
you.
3. Can you guys hear us all right?
Yes. thank you,
Perfect.
sir. So let us know when you're ready, and then Kayla will start the timer. Ready, Kayla?
All right. Good afternoon, everyone. Thanks for joining us today. I'm Shamir,
Alex.
and this is our first hackathon. So a little bit about us. We're incoming PhD students at Morgan State University for the Secure Embedded Systems program starting this fall. Currently, we're computer science seniors at St. Mary's College of Maryland. We both have Linux Plus, and we've taken multiple DAU courses, and I'm also a D'Souza Brent Scholar.
So just to start to get into our data pre-processing techniques, to start off with, we used the application RoboFlow to help import the data set. And so we had an excuse to look through each and every picture manually. We did manually annotate all 21,000 images of planes multiple times for both our models because, as you mentioned, garbage in, garbage out. We wanted to make sure to eliminate a lot of the potentially problematic images, which we do include later in the presentation. So this is our model health data in RoboFlow. As you can see, and as was mentioned, the American fighter jets tend to have an overrepresentation. We did try to address this by making some duplicate images for the more underrepresented classes, which I noticed were typically the more foreign aircraft, which we feel are very important to recognize because since we are making this for the Navy, we probably know what American planes already look like. So we made sure to duplicate with some pre-processing techniques, such as flipping, to ensure that the image isn't an exact duplicate for the more underrepresented classes.
Another big aspect of this project was the data cleaning that we had to do. So like you said earlier, we went through every single image and we annotated every single image. Surprisingly, there was a lot of really weird images. For example, a lot of text overlay, random people, lots of political leaders. Putin and Kim Jong-un were in some of these images. And a lot of these images also had some sort of distortion to it, low resolution, or some sort of editing that just kind of made it hard to see as a normal person. So we were able to exclude some of this content to clean up our data set.
Yeah, and beyond just the blurry images, there were also images that had like been intentionally distorted with for example, there's one with a cat that's been edited right over half the plane, which obviously would not be a good picture to try to identify or assign to a category. So for our image pre-processing, this includes the resizing images to 640 by 640 with a maintained aspect ratio. RoboFlow actually helped us with this. They have these steps in their default pre-processing techniques, which is another advantage of using the RoboFlow site. We also made sure to, as we said, keep the aspect ratio of the bigger images as it was touched upon before. The sizing of the images was fairly inconsistent.
And another big aspect was also the auto orientation. So whether
Yes.
the photo was taken in portrait or landscape, making sure we normalize it across all images to standardize the data set. So now let's hop into some of the model architecture and the design. So we created two different models. Our first model is an image classification model. So for version 1, our model type is RoboFlow 2.0 multi-label classification. So what that means is essentially it can assign multiple labels to these images, so we can identify multiple aircraft in just one image. And for version 1, we decided just to use the full data set. So we kept all 21,000 images. We applied the recommended pre-processing steps, so auto orient and then the resize, and we stretched it to 640 pixels. And we didn't apply any augmentations because we wanted this to be like our baseline model.
And the reason, our reasoning for making two different models, one of image classification, one of object detection, is that we wanted the user of our application to have options. The object detection model would be able to work as we are using the YOLO algorithm or architecture. It would be able to take in a live stream. We don't have that capability right now in our demo. However, the image classification would just be able to classify an image. So we wanted to have a high accuracy image classifier and also one that could be built upon for live stream or video analyzation and annotation.
And so that's why for version 2, we applied a lot more augmentations. So we tripled our training data set. We also added some flipping. So we flipped it horizontally and vertically, applied 90-degree rotations, clockwise and counterclockwise, and applied some grayscale to 15% of the images.
And our reasoning behind the augmentations is, having looked through all the plane images, we try to best augment the pictures according to the images that it was most likely to get trained on from the training data. So a lot of the planes images in the training data were duplicate images flipped already. So having the horizontal and vertical flip along with the rotations helped. There are also a lot of them that were blurry and a lot of grayed out pictures of planes. So I think having the grayscale to help our testing data prevent false positives is definitely pretty important. And then these are our object detection models with YOLO. Now the drawback for version 1, which is much different than version 2, is that it does take much longer to train. I think the YOLO NOS object detection took us about 36 hours of training before we could actually include it in the project. And this one we did add the blur because we realized in our image classification there were a lot of blurry images that we could still recognize as planes. The rule of thumb we went by is if we could identify it as a plane, we would include it. If it was unidentifiable as a plane to us, there's no way a machine would be able to identify it. So we realized that we had forgotten to include blur in the previous model training. So we definitely wanted to make sure that blurred images are going to be tested, used in the training data, because there were most of the images were at least a little bit blurry.
And I also want to note, for version 1 of our object detection model, it did have almost 71,000 images.
And this was through a feature on RoboFlow that auto augments the some of the sample data and making it a little bit different than the original image and then retrains it. So I believe there's a stat that yes, outputs per training example is 4. So we're roughly quadrupling our training data with the pre-processing with this pre-processing technique.
Now for version 2 of the object detection model, we did switch the model type to RoboFlow 3.0 and reduce the number of images in the data set, making the output per training example just 2. Still applied the same steps as previous. Unfortunately, we did not get the result we expected, and we'll dive into that a little bit here.
Yes. So for our initial data split for image classification model 1, we went with the default 70-20, 10% split. Model 2 is built on the trained model 1. And so we were just adding more pictures to the training set to see how robust the RoboFlow or see how robust the model would be with additional training data and using different testing images that we maybe hadn't used before. And then this for object detection model 1, which is with the 70,000 images, we initially defaulted to like an 85 15 an 80 15 5. However, with the addition, like with quadrupling the data, most of that ended up going to training for some reason. I'm not entirely sure of the reasoning, but we did manage to fix that issue with the model 2, which we did find to be a little bit more accurate, I think, than model 1.
So here are the results that we got from each of our models. I will say for both the image classifications, the accuracy is slightly inflated. we did externally test with images that weren't included in the data set at all that we just pulled off of Wikipedia. And we did get pretty good results, and we'll show you that a little bit down the road. And for the object detection models, they don't use accuracy explicitly. They use 3 other metrics to measure. So they use average precision, and recall to measure their effectiveness. But overall, we found that the models were pretty accurate and they were within our range of what we expected.
Yeah, I will say the accuracy, I think, is influenced in the image classification because some of the data that we were trying to test is if we could identify multiple images of multiple different types of aircraft. It's good at classifying if there are multiple like F-15s in an image, but it's falls short trying to classify blurrier images specifically and images of multiple planes, which wouldn't be in our testing data, which is why we believe the accuracy is so is inflated. I think the real accuracy is probably closer to the object detection model V2.
So now let's look at the component design choices that we made. As the previous group mentioned, CNN and YOLO were very popular, and we decided we would stick with what we know. I think they gave a very good introduction into what CNNs are. Honestly, the biggest issue we were looking at was being able to look at the images where it was only focused on one part of the plane and we couldn't see it in its entirety. So how do we bridge the gap when we're only looking at a specific feature of an image? And CNN seems to be working the best for us right now. We coupled it with YOLO 5, which really helped improve our accuracy and also keep the training time down, which was our biggest issue. As you mentioned earlier, in the one model that had 70,000 images, that took 36 hours to train, compared to our fastest model, which only took 2 hours.
I will also say that one of the main issues we ran into with this data set is because we decided we wanted to be able to have like an advanced level of familiarity with our data set that we're testing on. We had to go and manually label every single image that we included, up to about 20,000, I think, that we included, with the 1,000 or so filtered out.
And I will also add that we chose YOLO 5 version 5 and not version 9, specifically because we found documentation that supported it was better at quickly training and processing our images compared to ResNet, while still maintaining the accuracy levels.
And then moving on to our object detection model, which features YOLO NAS, which is a neural architecture search. YOLO itself is not like a complete neural network like something like ResNet 50 would be, where it's pre-trained, you can load it in and train it on the data set. You need like a pipeline for YOLO NAS and YOLO architecture. RoboFlow helped us with that part also, specifically bridging CNN and YOLO NAS, because it's not just YOLO NAS that we're using in the object detection models. But one big advantage of using YOLO NAS versus YOLO V9 is that YOLO V9 does tend to have a lot of false positives with their object detection, and you need something to kind of cut down on the false positives. So using YOLO NAS, which combines the YOLO architecture with the neural architecture search technology, helped a lot with reducing our false positive rate.
So if we had more time, I definitely think there's a couple of improvements we could have made. One of the big issues we ran into was Mac OS support. I'm on Windows and he's on Mac, so going back and forth, that was kind of an issue. But luckily we were able to work through it using a virtual environment. And eventually we decided we would just completely cut trying to support Mac, just focus on Windows for right now. Another thing I think we should focus on is the actual infrastructure. Uploading it to cloud, maybe using some hardware accelerators to speed up the pre-processing and the training times. And I think the last big thing that we were a little disappointed on was our live video feed integration. If you want to explain more.
Yeah, I spent a little bit of time on it yesterday with the time we had left in between training models. Our demo has had full video upload functionality. We just got caught up on drawing the bounding boxes in the video frames. However, we are able to do that. This is something that can be done. We just needed a little bit more time to get it done. I'd say like 3 days, and we'd be able to have live stream compatibility. And so one of our current limitations is our scalability, because the way we reach the RoboFlow inference, we have to send out a ping to RoboFlow servers because that's where our model has been trained on. So we can't just load up the model in our code. We have to send out what we want to be identified. So we would foresee especially because we haven't used any Docker containers, we would foresee in the future, if this was tried to go large scale with this, bottlenecks and slowdowns when trying to actually get your annotated image, just due to the nature of having to reach a different server and then ping it back to you. Alternatively, you wouldn't be able to use this right now without Wi-Fi. So
Okay. We also implemented some security features. So we added some basic authentication for login, stored the passwords with hash and didn't hard code it. Also stored the API keys in an environment variable. This is just for preventing any exposure.
and
Just speed through this a little bit.
yeah, we want to get to the demo. We made the site modular. It's very easy to, each HTML page has its own styling. Each script page has its own section in our project breakdown. So it's pretty easy to expand on.
And we think economically it is a pretty feasible option. We use a lot of open source technologies like Flask and Bootstrap, which kind of offset some of the initial costs, but there would be, included costs like maintenance, security updates, and any other new feature developments. There also would be operational costs if this was brought to a large scale. Deploying it would be a little expensive, especially if it was put on a private cloud or a dedicated server.
Time.
Now, as for potential applications,
That was your 15 minutes.
the demo?
Briefly.
Sorry, that was your 15 minutes.
Well, the demo is included in our upload, and it comes with a .bat file. You can run it straight from the app.py, but you can run the script and it'll open it up automatically.
Yep.
And judges, if you have any questions.
You mentioned using RoboFlow. So this was a cloud-based solution that you were able to use for your pre-processing as well as for the training of the models?
Yes.
Do you know what type of hardware they're using on the server? Oh,
I believe it's with like NVIDIA Edge.
okay. So they're just using some GPU solutions. You mentioned if you were to bring it more locally that you could, then of course you would run into the problem of needing like a GPU or something in order to make it run a little bit faster, right? So, okay. That's all I think of for right now.
So with your guys' implementation of RoboFlow, when you did all your data pre-processing, was that already pre-built into the RoboFlow software or?
Kind of.
Yeah, so like kind of, but no. So when you generate the version, like the final version of the model, you can just follow like the recommended settings or you can add your own. We decided for pre-processing, we would do what was recommended, which is the auto orient, but then we added the resize. So
Okay.
RoboFlow does it for us, but you do have to go and select it.
And in our demo, we do have several pages showing model visualization with our graphs and Epic losses over Epic training. And we have code visualization where we show how we're doing the upload function, how we're getting the inference, how we're hiding the API key and security features, et cetera. There is we wanted the demo to be also like a standalone presentation for convenience. So there is a lot of information there. I'd highly recommend looking through it if you can.
Okay. And with you guys said you did your resize, so that's where you did your 640 by 640.
Yeah.
Was that, did you guys pad that at all? Or did you guys how did you make that work? You said you kept the aspect ratio the same.
Yeah. So we did add padding to it after the resizing.
And that was you guys personally did that through Python or?
RoboFlow does not do that for us.
Okay.
Hi, thanks for that. I wish you had left your slides up, even though your time was over. I don't know what that's about. Can you talk a little bit about, thank you. You had the last slide you were. Okay, there we go. We had two mics on. Can you talk a little bit more about the economic feasibility of scaling this?
Yeah, so we imagine that this would take a lot of cloud computing resources. Putting it up on a large scale server, especially when a lot of people have to access it, that takes a lot of compute, takes a lot of time. Especially training these models. Each time we, maybe want to add a new class, or we just want to modify a previous plane that was already uploaded, that's going to significantly increase the costs. Each time minimum is going to be 2 hours to train a model.
Did you take a look into any of the techniques to maybe to shrink the model down to make the um, um, running the model simpler, like quantization type techniques? Did you look at that?
So we wanted to experiment using a couple different model architectures, which is why we have some YOLO and NAS iterations with the object detection. But if you look, if we had left it up, our second object detection model version 2 is actually trained on using RoboFlow's CNN architecture. So and just doing that, switching from using the YOLO NAS pre-processing technique or architecture saved us, like, it was a 6-hour train versus a 36-hour train. And then of course, if we had a little bit more time also, we would have gone through each of the images again and applied a more advanced filter. Because even with the ones we included, there are some that I feel like could be further removed or there could be some further filtering done to improve the accuracy there. Oh, and we also didn't touch upon it, but we do have a null class for anything that's not a plane.
Yeah, that's a good point to make, because like I said to the previous group, classification algorithms often can have they could misclassify. Another question is, did you try again validating the model on images that were not planes outside of that? And okay.
Yeah. So we pulled images off of the internet that were not included in this data set, mostly like from Wikipedia or whatever, like Medium. And we were able to classify those images. I will say for images that had multiple planes in them and different types of planes, that's when it got a little bit trickier and we saw a drop in accuracy.
Yeah, that's one of the main reasons why we think the 99.6 accuracy on our image classifier is misleading, because 99% of the pictures that are uploaded are single image pictures of planes.
Okay, coming over here because it's easier than passing the mic around. I'm kind of familiar with RoboFlow. I know they have a lot of auto ML tools. Is that what you guys use to decide which model architecture to use? Like just let the auto ML and RoboFlow choose for you, or did like I know you tested a few, but
So we actually took a class at St. Mary's, which uses RoboFlow to make machine learning models, but we were working with the instructor as our advisor for this project. And so we were talking over what techniques would best approach what architecture to best approach the project with, which is why we ended up going with image classification first and then switching to object detection when we realized maybe we'll have the time to get an object detection model up and running, because we knew the RoboFlow CNN networks were going to be quick and relatively accurate versus the more experimental YOLO NAS.
Any other questions? Okay, thank you. So our next team is going to be online. That's feature and edge aircraft classification. I think that's Desmond. Okay. So Desmond, I don't know, do you have any other team members or is it just you, Desmond?
I think it's just me.
Okay, but we are ready when you are. Just let us know when you're ready to start.
Okay. Am I good to share my screen?
Yes.
Okay. Share. And then let me present. Okay.
Yes, we can see your screen.
Okay. Am I good to present?
Yes.
Okay, cool. So hi, everybody. My name is Desmond Eastep, and today I'll be presenting the research slash project I've been doing for the hackathon, which is dynamic volume features slash edge detection in motion. Before I get into that, a little background about me. So I am a recent graduate from North Carolina A&T. I'm currently working at Navair. I just started February 28th. And some of my hobbies, which is why I really like this hackathon, is robotics and also playing around with drones. And I really wanted to explore and get some background on the AI and ML side of it. So, and then another background thing as well is actually before I signed up for this hackathon, I actually read about a drone attack, which it's labeled as like Tower 22. You can look it up later if you want more information about it. Where actually 3 US troops were killed due to inadequate air defenses and specifically classifying what was actually an enemy in the field. And I think this challenge is really cool because it gives an opportunity to kind of solve some of those issues that are being seen in the war fighter. So I really like this challenge. And then getting into what is actually dynamic volume. So you probably heard me mention feature and edge detection in motion. Okay, what is that? So the 3 categories I chose to use in order to model and train on was actually feature extraction, edge detection, and also doing some pre-processing techniques, not exclusively, but some motion blur in there. And with the feature extraction, which I'll explain in some of the later slides, I used a feature detection algorithm, which is called like Shy-Tomicide, to kind of do some extra extraction of any shapes and textures of something that might be an object in free space. And then also some edge detection so you can get a better outline of what the aircraft or air vehicle actually is. And then, as I mentioned, too, the motion blur, and I did that in a couple different directions just to give some more of our variety and conditions for the data. And so going into some of the pre-processing I did, so some of the pre-processing I did, and which you can also see to the right, is I did resizing. I also played with some grayscale, some noise reduction and using some Gaussian blur, and also doing some normalization and some contrast enhancements for the images and seeing how all of those would actually affect the model and affect training it as well. And then going into some more of like feature and edge extraction and some of the results I had. So as I mentioned earlier, I use some of like OpenCV's libraries where they actually have a good features to track function, which uses like a Shy-Tomicide corner detector. And this basically over any objects that thinks it might be an object or any corners that think, okay, yeah, this is probably an object. It kind of puts dots or really puts a note of like, hey, this is probably an object, which you can see kind of or you can see in the image to the right, where you can see the blue dots and how it's recognizing that, hey, this is an object of interest. And then going into the edge extraction of it, what I did is I actually used a canny edge detection and getting some of those edge features to also feed into the model. And you can see that it gets a couple outlines of the image. And I just used one of the images in the data set just to represent what this is actually doing. And this will give a better outline for the model and give some more features that it can detect on. And so the model architecture that I used for this was I just used a convolutional neural net. And the reason why I use this is it's a little easier to manipulate because I actually did think about using the YOLO, you only look once architecture. But due to the time constraints, it was a little hard to modify that to also put in the feature and edge or the edge detection that I wanted to for the model. So I stuck with this and just did some slight modifications. But other than that, it's the typical convolutional neural net that you've seen in some of the other slides and typical in machine learning or image classification. And then for the training, so for the training, I had a couple of issues. So when I was training the model, I tried training it 3 times and I used Google Colab and I also tried Kaggle. It had a timeout issue, like when it got to, I want to say the 50th iteration. So what I decided to do was I had to reduce some of the data set or some of the images that I was using. I think I used about 200 images and I split that in 70-30 as a data set split. And so some of my values or some of the results I got are a little skewed just because I used a smaller subset of the main data set. And what you can see that in this next slide as well, where you can see it only achieved around 60% accuracy, which it's probably a lot lower just due to the reduced size of the data set. And I use some inside TensorFlow functions just to graph what I was actually seeing in terms of the validation and training accuracy. And I guess going into some of my future thoughts and some of the things I would do in the future doing this is one of the main problems I believe it was happening when I was actually training the model was adding in the feature and edge detection was a bit too much for the convolutional neural net to process, especially since I modified some of the layers. And I think what was happening is over time, there was a misprocessing of the data and tensors weren't actually matching up with one another. And so it just timed out once it got to a 50th iteration. The thing I would like to do next is kind of modify those feature inputs in order to make that go smoothly through the model better. And then also, because this is mainly just detecting on still images, one of the things I thought too as I was researching was doing optical flow, which is actually comparing one frame to another frame and seeing how the object that it detects is actually moving between the frame to identify motion or a moving object or to identify moving objects better. And also the third idea that I had for the future was also doing some motion labels, just so you can see how things are moving for more field feasibility. And I think that's pretty much it for my slide. I did actually want to show a demo, but I didn't realize that we could show a demo. So I actually had started another training session just to see how it would work, but I kind of have some of what the feature and edge extraction was doing in the previous slides. But yeah, that's it for me. Any questions?
Thank you, Desmond. We'll open up for questions.
Hey, Desmond, thank you for the presentation. So sort of one of the questions I've been asking so far is just, so what, did you look into the data set and investigating the biases?
Yes, I did, especially when I found out that the model kept stopping. I did see that there was a bit of a skew because the other teams I mentioned it earlier, a bit of a skew towards American aircrafts. And also, as I was speaking about the Tower 22 incident, there actually wasn't any like drones or like UAV type of vehicles in the data set as well. And as I was testing it, I tried to put some of those in there just to see how it classify on that and add an extra label just for UAV and some of the drone types.
But that sounds good. What about the accuracy rate? I don't think I'm not sure. I don't remember if I saw the number. Was it something like 60%? Is that what I saw?
Yes. Though I would say that's a bit skewed just because I had to reduce the size of the data set to get a completed trained model. In the future, I would like to actually train on the entire data set to see how the accuracy really is adding in the feature and edge detections.
Okay, and did you try validating the model with pictures and or images that are outside the data set?
Besides mainly the UAVs, then just for testing, I took some random aircrafts offline, or I mean online, and just looked up what they were and put some of those into the data set to kind of offset the data, some of the data set I didn't use. But that's mainly what I did with that.
And when you did that, I'm just sort of to make sure I understand. You would expect that if you put something in there like a UAV, which is outside the data set, that either it would classify it as an other or maybe as something else, or but not false positive or something. Is that what results did you get?
So when I put the drone in there, because the label I actually had used for the UAV is I actually just put straight up like a UAV label as I was classifying it. I kind of got mixed results. Like sometimes it would classify it as one of the aircrafts in the data set, and sometimes it would classify it as that other label, which was just UAV. I think in the future, I would like to actually have a more robust data set with some of those other aircrafts just to reduce the false positives I got, both with the UAVs and also with the aircrafts that were in that data set or just aircrafts in general.
So I don't think I quite understood. So did you actually then train your model with some additional data that you pulled with these UAVs?
Yes.
So you just augment the data set. Okay. What about other pictures? Did you try like maybe try in a car through there so that's um, see if it classifies a car as an aircraft or something?
I did not. I mainly focused on just flying vehicles.
Okay. Thank you.
Any other questions? Ryan?
We have a question from what about hyperparameters? Did you ever play any with those?
Any hyperparameters? I did not know. Also, I'd like to ask a question. What exactly are hyperparameters?
No, those are your learning rates, those sort of parameters that are the inputs to their model when you're training.
Oh, gotcha. No, the only parameters, because does that include the batch size and the epochs as well?
Yes.
Okay, I did actually mess around with the batch size and the epochs. So originally, I tried a batch size of 32, and then I switched over to a batch size of 64 just to see the result of that. For the batch size, when I doubled it, I actually saw that the model got less accurate. So this probably should have should have put in there, but when I reran the code and it regenerated this graph, I actually saw that the validation accuracy was leaning more towards the 0.5 as well. Other than that, I tested different epochs just to see if it would actually train the model past the 50 iterations before crashing, but unfortunately that didn't work either.
Another question is, did you talk about the data splits, like what your training, validation, and testing percentages? Okay, thank you.
Did you still need me to answer that, or?
I think no. Apparently, you did. I'm sorry, I must have missed it. What about the economic feasibility?
So for the economic feasibility, mainly the way that I see the economic feasibility going is if you have these systems out in the field, you would need a pretty expensive camera because you will want the highest quality, or I guess what I'd say the highest definition camera. in order to be able to see aircrafts in the sky? Because I'm assuming, using these types of data sets, you will want to use it on targets that are either in the sky, very far away, or moving targets as well. I think in terms of pricing, because I know I've seen some systems just around the base, I would say like the camera would probably be like up to $1 million or so. And then you would probably, for the training aspect in general, you would probably just need a decent PC or something with a high GPU. Would that be like $2,000 in terms of like training costs? I would think if you need like a high amount of data to train on this, you may need a couple of those. So maybe like a server farm. That's what I would think about in terms of economic feasibility.
So I have a follow-on question. If
Yes.
the purpose of this is to be able to identify aircraft that you might not have a great photograph, right? Which I think is the purpose of this. Why would you need $1 million camera?
The reason I say that is just based off of systems that I've seen around, or at least on base. And the reason I would even say that is I think at some point, if you have too low resolution of a camera, you wouldn't be able to get any distinguishable features to actually detect and classify on the models. I think the goal is definitely to work up to that, but in order to be able to have the best chance of classifying the aircrafts in your environment, I would say, at least from what I've seen, I don't want to say that's the standard, but that's a good route to go. But again, I'm not extremely knowledgeable on camera costs, so that's my best answer / guess at that.
Do you think if you're able to get your like any kind of model to work off of a low quality, would it work just as well on a higher quality camera?
I believe so, unless like the images are just extremely distorted and the model starts to train on features that are not actually representative of the aircraft. But I think that's definitely doable, especially if you clean up the data using, normalization, some Gaussian blur, and just process techniques to make sure the image is, as stable as possible before feeding into the model.
Thank you.
Any other questions? No, thank you, Desmond. Thank you very much.
Thank you guys for your time.
So next we have the aircraft detection model team. That's Hassan. Hassan, you're still there. When you can share your screen as you need to and let us know when you're ready. And I don't know if you're speaking because we can't hear you if you are. Okay. All right. I see your chat that you're trying to address your audio. For benefit of our audience, Hassan is out of the country. Hassan, someone suggested that you might be able to call in if your audio is not working. Were you able, was it still dialing in? Or did you get a connection? We can't hear you still. Still dialing. Okay, we can see your screen now. Someone is suggesting.
Hello?
Yes, we can hear you now.
Okay. Awesome. It's coming through properly, right? Like there's not too much lag. Hello?
I'm saying, we can hear you.
Oh, okay. Awesome. Well, let me get started. All right. Before we start, I just want to thank you all for giving me the opportunity to participate over Zoom, especially given that currently I'm out of the country and I'm in London. With that being said, I would like to apologize in advance for any connection issues or audio quality issues that may arise as a result of my current situation. That being said, my name is Hassan Ture, and I'm here to present to you a data-centric approach to military aircraft recognition. So a little bit of background information. We need to discuss a few definitions here. For example, let's start with the definition of a model. In this product, a model is a neural network. Neural networks are sets of nodes that form layers. These nodes and layers are connected and work together to perform a certain task. The idea of a model is based off the idea of a human brain. For example, you can think of a node as an individual brain cell, and you can think of a layer as a tissue or a region within the brain. That being said, these nodes work together but are also interdependent, and these regions are clusters of nodes that control different tasks and different computations within our model. Layers can be defined into three main categories, that being input, hidden, and output. Input layers are where the model first ingests the data. An analogy of that could be our senses. So like, for example, we have our nose, we have our taste, we have our ears. These would all be an example of our input layer, as this is where we're taking information in. An example of a hidden layer could then be seen as our brain, where the computation actually occurs. After we've gathered some stimuli from our senses, our brain then makes ideas and thinks for us. So then we can then transfer into our output layer, where the final decision is made based on the previous layers. Our output layer could be like our reaction to the stimuli. So for example, if you smell something you don't like, your nose would be your input layer. The hidden layers are your brain cells and your actual brain. And then the output layer could be the result of you maybe lifting your shirt to cover your nose from the interaction. A little bit more background information. The idea here is that we are representing images as matrices. And within especially the hidden layers, we are doing computations on these matrices to better extract edges and features from the objects we're trying to detect. The main way that this is done is through mathematical computations that are represented by matrices, as shown in the middle. We have an image of, I believe, Abraham Lincoln on the left, some matrices applied to it, and then another image to the right. So, though this is a data-centric approach, the model is still an imperative choice. My model of choice was YOLO V8. YOLO stands for you only look once. This ties into it being a one-shot detection model. With that being said, that means that our image will pass through the layers of the model only once. This ties in well to real-time applications, as our detection time is actually very low as a result of this. Now for our model training. Multiple models are trained as part of an iterative process to improve model performance and highlight different data preprocessing and augmentation techniques. In order to train models, a Google Colab environment was used. This Colab environment provided me with more training power and computational storage that I would have locally, at least for this project. Our training environment also utilized transfer learning. The idea of transfer learning is like giving our model a head start. So for example, instead of me training a model completely from scratch, which would have taken me many more hours than what I originally put into this, we're giving the model almost like a chunk of a different model's brain in a sense, where now that we have that beginning chunk, we can then build off of that beginning chunk, so our model can now observe higher level features. And finally, but not least, let me move this. The model was trained primarily on photos of A10 warthog images. Reason for this is that a lot of other subsets of data were spawned in as a result of my data augmentation techniques. And the subset here, that being the A10 photos, is enough for me to display a proof of concept, if you may. So pre-processing. Prior to training the model, steps were taken to clean and organize the data. After downloading the data set onto my computer, new directories are made for each of the aircrafts that appeared in the data set. So the data set originally came in with unique identifiers and the images and their corresponding CSV files out of order or in an order that wasn't really palatable for me. As a result, I remade some of the directories and moved the images and the corresponding CSV files into their appropriate directories based off the aircraft that is being represented in the images. After that, I created text files for each individual CSV. These text files were used to appropriately train our YOLO V8 model. The text files use information from our CSVs, and this information is used to then generate the appropriate information that we need for us to then train our YOLO. And these actions were all done via the use of Python scripts. Before moving on, the photos and their corresponding text files were moved into training and validation directories onto my computer, once again via Python scripts, prior to them being loaded up to the environment and being trained upon. So a little bit of some background on our pre-processing and data augmentation. Some augmentations that I did to the photos included canny edge filtering, contrast changing, black and white, so changing it to grayscale, and blurring, that being Gaussian, median, and bilateral. The reason this was done was so that each individual model could specialize in detecting certain kinds of images. This was also done to help reduce noise in some photos, and this can help highlight parts of photos that are important for models to detect aircraft. Here's some examples of augmented data. Moving left to right and up and down, we can see that we have our original photo, black and white, contrast, where the brightness between pixels has been greatly changed, canny edge, where similar to our example earlier about how our hidden layers apply matrices as computation, a particular filters such as the FOBA filter are passed onto the image so that way we can properly extract the edges from the image. We have bilateral blur, median blur, and Gaussian blur. These blurs are the same idea where a matrix is applied to the image in order to blur it. However, bilateral blur is better at preserving edges. Median blur uses the median value of the matrix as you pass over the image in order to give a new value to your image, or to the pixels in the image rather. And Gaussian blur is a matrix that is representative of a Gaussian function that once again is applied to the image. After training, here are some graphs to show the evaluation of my data. So the main idea here is that we want our loss functions to be 0, and we want our loss functions to be 0 as we approach our last epoch. With a little bit of background, a loss function is a way that we can represent what our model thought was true versus what was actually true. Two main losses that I was primarily concerned with here were our box loss and our classification loss. Classification loss is the difference between what actual aircraft is in the photo and what the model thought it was. And then the box loss is the difference between the position of where we put our bounding box versus where the actual bounding box is. Our main idea here, our main goal here is try to get this curve to be as smooth as possible and get it as low to 0 as possible. We can see here that we have graphs from our normal, contrast, canny edges, black and white, and blurs. Here are some detection examples and what it looks like when the models are actually running detection. Once again, left to right, up and down, we have original, normal, canny, black and white, so on and so forth. The idea here is that our normal detection occurred from a normal model. That being that the model was trained only on images that did not have any augmentation applied to them. This model was then used to detect aircraft within a normal photo. Moving to the right, we have our canny edge filtering, where a model that was strictly trained on canny edge images is then used to detect aircraft in a canny edge image. The same idea applies to black and white, Gaussian, the rest of our blurs, and contrast. So within this example, the original photo is actually quite nice. It has not too much blurriness, there's not too much noise going around, and it's quite easy for the model to actually apply detection. However, in real world applications, that's not always the case. Data can come in blurry, data can have hot spots in it where some of the pixels are lighter than others. Data can come in where, let's say it's even dark and the data is, it doesn't have many values to go off of. That being said, I have a script ready to demonstrate why it could be beneficial to train multiple models in order to combat this. Are you guys able to see my screen, or is it just on the PowerPoint?
We can see the PowerPoint slide or application, so I think we can see your screen. Over.
Okay. So hold on, let me do this. Okay, so here we have a Python script ready. So to start off, take a little while. All right. Are you guys able to see this clearly? I know it came through a little small.
Yes, we can see that.
Awesome. All right. So here to start off, we have the same image from before. We have the normal image being tested against the normal detection model. As you can see, it is able to successfully detect the model. The image, like I said before, it's quite clean. It's quite easy to do detection upon. However, in real world applications, images are not always going to be clean. For example, the image could come in darker for whatever reason, or if you want to even think about it like this, the image could be taken at night where the brightness is lowered. As another example, I lowered the brightness down to 5% of what it originally was and tried to run the same detection model on it, but it failed to detect. Now, in order to circumvent this, you can actually use data augmentation techniques on this poor image that we've collected in order to bring it to a standard where one of our models can successfully detect it. So for example, here, I decided to go with candy detection in order to extract the edges from it and then apply the candy detection model onto our new augmented photo. So as you can see here, the candy detection model was able to accurately detect our A10 planes when the photo was correctly augmented into its appropriate form. So moving back into the PowerPoint. Give me a moment. Current slide. All right. So proposals or improvements I would try to accomplish given more time. In order to develop a model that can detect objects in a wider spectrum of images, I would combine the separate models into one. This will be done by training one model on the same data set plus augmented versions of each normal photo within the data set. This will result in one compact model that is more adept at detecting aircraft. Second, I would develop a system that can be used to semi-automate the augmentation of data. The system would allow the model to know what augmentation techniques to apply to target image to help detection. So for example, let's say the image comes in and it's very dark. The model could be able to take the average brightness of the image and make adjustments to it in order to bring it up to standard and try to run a detection again against itself. Another thing I would do is I would expand the training to other aircraft along with A10. Finally, I would add more pre-processing techniques such as image subtractions and changes to brightness. Some potential applications of this would be that we can use real-time threat detection. That being that because we use a YOLO V8 and it has a low detection time, the time that it takes for us to input, process it, output it, and then for us as humans to make decisions based off that is minimized. We can use it as for tasks in the field that may include image collection in nature. Of course, collecting data from people and really just data in nature can be very messy at times. It's not going to always come in clean. So having a resilient and flexible model like this is very important. Finally, but not least, we can task this model with video surveillance. Videos are essentially just images that have been put together via frames, so that way we get the idea of motion. In that sense, we can break the video into its individual frames, apply augmentation,
Hassan, it's 2
and then
minutes.
put these thank you for the reminder. And then we could put these augmented images back together in order to make an augmented video. The same idea can be applied to detection. We simply break up the video into its individual frames, apply detection to each of the individual frames, and we put the video back together in order to get a video where detection has occurred. I would like to thank you all for your time, and does anyone have any questions?
Thank you, Hassan. Judges, questions?
So you said you primarily did this with A-10s. Did you ever try this with other aircraft?
So at least when it came to separating the model, the actual models were built on A-10s. However, I did test my A-10 model against a few F-16s that I actually was able to get off of the internet, so images outside of the data set, and no false detections were thrown. I also did apply this to a wooden boat image, and once again, no false detections were thrown.
So a little bit more about that. You said you just tried a few, but you had access to the entire data set. I'm curious as to why you didn't use the rest of the after they were in the data set. Over.
Right. So given my resources and my time, training on the entire data set, at least with the approach that I was originally using, I found that it would have taken me too long for me to put out an acceptable project, given how much time I had allotted to this. As a result, I ended up pivoting to using a subset of the data set more as a proof of concept that if it can work with this, then there may be a few hurdles for it. We're going to a larger data set, but at least we have step one done.
Yep, that makes sense. I understand the limitation of hardware for sure. For the large data set, lots of different aircraft that could be difficult. So going down to a single A-10 or a single classification class is not a bad approach. But still, you could have validated potentially with taking a sampling of an aircraft from the data set and fed it through it, and that would have been an interesting result to get. So thanks.
Okay, thank you.
Yeah, and to a similar point, so I understand that one of the limitations of having limited the data set to A-10s is you sort of miss the validation opportunity, as I understand it. But in thinking that through, did you identify any other potential limitations? Maybe I'm just too close to it. Did you identify any other potential limitations to having limited the data set only to A-10s? What else was missed potentially?
So some potential limitations was, of course, just having a more powerful model that, this being, the whole point of this being that our model is able to detect images on a wider spectrum of, is able to detect aircraft on a wider spectrum of images. The spectrum at which this model detects is narrowed. On top of that, I was worried at times about the idea of overfitting if I only had one model trained, if I only had one aircraft in my training data set. Would the model then only be able to detect that? Would the model then only be able to detect that, and would it always detect that? However, I was fortunate enough to get my loss functions to an appropriate point where it wasn't overfitting, but at the same time, it was at a comfortable area to do detections.
Thank you.
Any other questions, judges? No? Okay. Well, thank you, Hassan, for your presentation.
Thank you.
And next we have aircraft detection. I think, is that Andre?
Okay. Yeah, I was muted. I'm sorry I missed the introduction. My name is Andre Sampello, and together with my colleagues, Christopher Van Hook, Donovan Lowe, Gerald Little Jr., and Lucine Kamikian, we worked on aircraft detection and segmentation. Just a quick overview of what I'll talk about today. I'll quickly go over a problem statement, get into data preprocessing, into modeling, and then what we would do with more time. So some of the challenges that projects like this could help solve are areas like security and threat identification. For example, knowing where a specific aircraft's country of origin is, or even like detecting anomalous aircraft. We also have a lack of data. So there's also the potential to create more data for other models to use and leverage and just get more value out of some data. There's also models these days are getting pretty lightweight while maintaining some pretty good performance. And this increases accessibility of models in remote areas and on edge devices. We propose some solutions to take on these challenges, usually leveraging object detection and segmentation on military aircraft. We also created a user-friendly AI to help aid in data labeling efforts, as well as choosing models that specifically could run on edge devices, minus the segmentation model, but I'll get into that later. So for the data pre-processing techniques, one way we could squeeze more value out of our data is to apply some augmentation. This is a very common strategy in computer vision. This helps in a lot of ways, and it can make our models more robust. For example, to different lighting conditions, to different orientations. You're just giving your models more examples of your data. You're squeezing, you're getting all of this extra value for free. And along with that, we also, for pre-processing, we had to convert the provided Pascal VOC format to the YOLO format, because we do, as you'll see in the next slides, we use YOLO. So in a nutshell, our architecture design is as follows. We start by passing an image through an object detection algorithm, which is a fine tune of YOLO. We then use those bounding boxes for our segmentation model. For our segmentation model, we're using a model called Segment Anything. This is a pretty new model from Meta, and this will segment anything and everything in your image. We want to narrow in the scope of that segmentation, so we actually leverage the output of YOLO, and we only do segmentation on the regions of interest from that object detection model. Here's a little image of our UI where you can pass it an image, and in the right you can see bounding boxes, the classification, and the segmentation. And note that the segmentation does not happen on the entire image. It only happens within the bounding boxes. So for training and evaluation, we only really fine-tuned our object detection model. We decided to go with YOLO V9. It was the newest, and we only had a day to train, so we had to pick and go. It is a popular model, at least the YOLO family of models, for performance. And as aircrafts are fast, the ability to detect things in real time is important. So the size of the model was about, on disk, 450 megabytes, which is about 58 million parameters. Might sound big, but it's not too big. There's also mean average precision at 50. So this is at 50 IOU, the intersection over union. We had on our test set, we had a 0.83 metric out of that and a 0.74 for IOU 50 to 95. And we trained for 53 epochs. Here's just a couple of quick visualizations on some of the results. To the left, you can see F1 confidence curve, which is like a mix of precision and recall. And then to the right, you also have a precision and recall curve. And you can see the 0.83 mean average precision at 0.5. Here's just a quick viz for the confusion matrix if you're interested in looking deeper to the results. I won't get into it too much, but I added it here in this slide. So if we had more time, like a day was pretty short. Like we didn't have a lot of time to explore a lot of areas that we could have. So we could have benefited from additional data pre-processing. We did see that we noticed the data imbalance and we had plans to address it, but we didn't have time to implement what we had in mind for that. Along that, we had further model training. We did have to, like, I trained my model overnight and I actually woke up to an error, a CUDA error. So like further model training would have been good if we had more time. We would have also trained a smaller model with the segmentation data. So that segmentation output of our pipeline, you could actually use that to kind of get more value out of our base data, which is just bounding box data plus image. We could potentially leverage this to make more segmentation data and train a smaller model for segmentation. We had plans, or we had the idea of model quantization just to optimize more for performance. We had ideas for anomalous aircraft detection. So instead of just if an anomalous aircraft were to come to our system, we would probably just misclassify it instead of calling it an unknown aircraft. So that's something we had in mind as well, but we did not have time to implement. Some cool ideas also go into like country of origin classification, where we could locate some symbols maybe in the image where we could like indicate, which could indicate it's like its area of origin. And also aircraft class recognition, fighter, bomber, oiler, cargo. Yeah. So that's the end of my presentation. I guess I'll jump into a quick demo. So we are leveraging Gradio. This is running on my laptop. So it's not as quick as if you had a GPU. But you'll see here in a sec that it's not real time. We can pass in an image. If you click detect aircraft, it takes a few seconds, but you'll get a classification, a bounding box, and segmentations specifically in those bounding boxes. Yeah, that's all I got. Yeah, like the potential like impact of what everyone in this event kind of worked with over the past few days, like has the potential to help pilot safety and improve aerial security, which is really important work. Yeah, and I guess to close out, I would like to thank the Velocity X team for hosting the event. We are from the West Coast, but it was a fun challenge, and thanks. So yeah, I guess I'll open it up for questions.
Thank you, Andre and team, and welcome. So excited that we have a West Coast team participating. You're our first, so thank you.
Awesome.
And I'll open it up for judges.
Yeah, Andre, yeah, thank you so much for presentation. And this is a fun application that or GUI that you have here. I like it. A question that I've sort of been asking a lot is, have you tried pictures outside of the aircraft data set to see what the classification is? I think you mentioned that something like this, but could you go back over that?
Yeah, so we did not implement that here, but we did mention it in our if we had more time section. So yeah, not quite like extra background data, but potentially like maybe aircraft of different classes like that we don't know. Like we could label them as just unknown aircraft, not in our, on our list. Because if an unknown aircraft were to come into our system, we'd probably just misclassify it rather than calling it anomalous. So we had, yeah, that idea was thrown around, but we didn't have time to, to improve the false positive rate by introducing more data, like non-aircraft data. We did not get into that here.
No, that sounds good. Thanks. You mentioned you actually showed the confusion matrix, which I really liked. I like the confusion matrix and some of the other curves you showed. Did you investigate any of those? If you kind of see here, there's some areas that have 0.8 versus maybe that's maybe like 0.5 or so. If I could read your maybe 2.2. Did you investigate how that might be related to your data? Over.
We did not, but that would be a great, analysis step. This morning we kind of we had a scramble to get evaluations out. We had to wake up pretty early over here. But yeah, it's definitely wish we had one more day and we could have done more analysis. Just honestly, we didn't have time to dig in too much on the results.
Thank you so much.
So I actually was really sort of intrigued by this slide. I don't know what a confusion matrix is, but I'm intrigued. Would you mind just sort of saying a little bit more about what that is?
Sure. So along the diagonal over here, these are the correct predictions, right? So on the left-hand side, you have predicted. This is what your model output, and then you actually have the label at the bottom. So for example, you could, if you look at this square here over my cursor, if you can see that, this is talking about a case where the actual label was SU25, but our model predicted F14. So it's like you get all of this information comparing each class to each other. And yeah, along the diagonal are the correct identifications, if that makes sense.
Yes, thank you.
A couple more questions about any sort of pre-processing. Did you look? Uh-oh, looks like your antivirus is expiring.
Oh no, I gotta update that.
That's here.
Oh, that's nice.
It pops up all the time. Sorry.
So sorry. Did you investigate any of the data itself or any pre-process? Like, what was your pre-processing steps? I think I only saw a little bit of that. Can you explain any data biases that maybe you encountered? Or
Yeah, we did a little bit of exploratory data analysis. We we just eyeballed random samples from each class. We also noticed the imbalanced data set. But we didn't, we had plans on incorporating class weights so that we could scale our the losses for each classification based off of its frequency within our data set. So that the high frequency data points would have less contribution to the loss, and the the lower frequency data points would have a higher contribution to the loss. It's a very common practice to deal with data imbalance along with upsample downsampling. But we actually did not have time to implement that. Once we started training, we figured it was kind of too late and we had to roll with it.
I see here that you've got a background. Do you mind elaborating on that?
Background
On the bottom of the matrix.
on the bottom of the matrix. Oh, background. Yeah. I actually don't know. Oh, I think this was the this was out of the box with the library I used to train. It picks things that are outside of the outside of the labels, and then kind of calls it background. Yeah, this was not something that I manually did.
Thank you.
Yeah.
Any other questions for judges, from judges? Okay. Well, thank you, Andre and team.
Thank you.
And so next we have the last team, which is IR Aircraft Identifier, and that's Ari Gaskins. So, thank you all for sticking it out, and I so much appreciate our judges for your careful deliberation of the presentations today. And so we will get right to it. And we're going to announce the winners, and then we'll ask where appropriate for the teams to come up for a photo op. So without further ado, first place goes to the military aircraft ADML model team. That is Shamir and Alex. Congratulations. And I'm going to, we'll take one with the two of you and then with the judges. Oh, yeah, if you can. And you can actually, the velocity X. And you can delete that. You can just delete the box. Take the
Oh, that's when it starts to get. Oh,
you can take it. There you go. My brain is fried. And you know what, if you're able to, we'll take the pictures with the judges after we announce, so we won't keep the rest of the teams who are online. Okay, thank you, congratulations. So in second place, we have the aircraft detection team, correct? And that is Andre and the rest of his teammates, and I don't want to do a disservice. Andre, do you want to come off mute and introduce the rest of your team as well? Even if they're still online, you all can speak as well. But congratulations, your second place.
Hey, thank you. That's awesome. Thanks. Yeah, it's awesome seeing so much interest in the space. So my team is Donovan Lowe, Lucine Kamikian, Christopher Van Hook, and Gerald Little Jr. So, yeah,
Great,
it was
congratulations.
awesome. Thanks.
So Andre, we will be in touch with you and we'll need to get the information for the rest of your team so that we can send you the appropriate paperwork to get you your prize winnings.
Okay, sounds good.
Okay.
Thank you.
Thank you. Congratulations again. And in third place, we have Team Feature and Edge Contingency Model. I'm sorry, I'm butchering your team name, Desmond. You want to come off mute? Congratulations, your third place.
Thank you so much. I
Tell
enjoy
us your
this
team
job.
name again.
Oh, it's a feature and edge aircraft classification, or I guess in the slides I call it dynamic volume, but
Okay.
the reason I picked that, yeah,
Congratulations, third place.
thank you so much.
And that's $2,500. So same thing, you're familiar. I'll get you the paperwork so that we can get you paid or get your prize money to you. So look for an email communication from us next week. And then last but not least, we have fourth place. And in fourth place for $1,500, we have team 111%. Congratulations. Congratulations. So once again, congratulations to all of the teams. And before we conclude and let those who are online drop off, I've already given out a couple of certificates, but I just wanted to award some certificates to our other volunteers. So I want to give a certificate of appreciation to Dr. Sybil Anderson. Thank you so much for participating and being a judge. So thank you. We also have a certificate of appreciation for Kim Mazingo, one of our other judges. A certificate of appreciation for Jonathan Duque. There you go. Thank you. And then for Jonathan Fogler. Thank you. I'm sorry, Nathan. So sorry. Thank you, Nathan. Okay. And then one of our mentors who was not here, Monty Campbell, he was here as a mentor yesterday. And then I want to thank publicly Ellen Stravetnik. Ellen has been on this journey with us since August of 2023 when we first started meeting, and this was simply just an idea. I had this idea about AI, and so with Ellen's help and connections and the team, in particular, Ryan and Will, you, under your leadership of Dr. Ray and Michael Lay, made this come to life. So thank you all so much. It would not have happened without you. So yes, and Ellen has been faithful following up with me and on planning calls. And I also want to thank, even though they're not here, and I'll make sure I acknowledge them, Andrew and Michael, there's another Michael on our, it's Andrew and who else? Yes, on our planning calls. They have been on all the calls. So I want to thank the whole team that really, NOC AD made this happen. It wouldn't be possible without you. So, and the collaboration. So thank you to, and special thanks to Kayla for in past years, we've had a consulting team that has helped us with this hackathon, and this year it was Kayla and I, with the help of the NOC AD team, pulling this off. So it's kind of like doing it for the first time. We learned a lot of lessons, and but I think we're on a good track to continue with the success. Got a West Coast team, got a team from St. Mary's, and so we'll just continue to be able to spread the word and have more people know about this hackathon and what we're doing. So thank you, everyone. We'll have more photo opportunities. Thank you for hanging in with the late hour on a Friday. Teams that are online, we will be in touch for those. And I want to say thank you, Hassan. Hassan has participated in all 3 of the hackathons that we've had since 2022. So we appreciate you supporting, and also to Ari, who's not in the room right now, but once again, we appreciate the participation. So thank you. So that's it. We'll do a couple more pictures, but thank you.